All right. So I want to pivoting my plans. My plan was to talk to you about chapter 3 today. I'm not. You can watch the video. That's your homework. Watch me lecturing chapter 3 from last year. Okay, that will be your notes on chapter 3. I think we need to spend more time on the labs and linearizing graphs. Okay, so that's why it says first thing on our agenda is to finish the linearizing graph activity from yesterday. So could you all please open that Google Sheet up? The linearizing graph practice. For homework tonight, besides watching the video, it's 40 minutes exactly. You can fast forward a little bit because some of it is a discussion from what to do with Lab 4, but we're going to tackle that in class together. So you can just fast forward to the actual presentation of the notes for chapter 3. I would like you to read through labs 5 and 6 tomorrow. The reason I'm asking you to read through both is because I don't know which lab we're doing tomorrow. Lab 5 is an outdoor lab. So if it's raining, we're not going out. In which case, we'll do lab 6. Because lab 6 is an indoor lab. All right. So I need you to be prepared for both of them, either of them. And then the weather is supposed to be better next week. Monday is supposed to be absolutely gorgeous, 80 degrees and full sun. Tuesday is supposed to be a little cooler, but again, full sun. So if we need to do the outdoor, it's a 2-day lab activity that would be done outdoors. We would do it Monday, Tuesday next week instead of Friday, Monday. Really doesn't matter. Okay, does everybody have the linearizing graph Google Sheet open? This one here. This is where we left off yesterday. So we did all of example 1 together, correct? Okay. Then we did all of example 2 together. That took us 2 graphs to get to the final graph. Example 3, we had 2 graphs again. We were able to get to our linear graph with 2 steps, the original graph and then the linear one. Example 4 is not going to be so easy. We started by making our first graph, which was hyperbolic. We have that here, power curve. We don't care what the equation is because we don't do anything with curves. We need lines. So we tried to linearize that by doing the same step we did with graph 3. Let me see if I can make this a little bigger too. Just kind of reviewing again what we did yesterday. There we go. So this is the graph that we have now. We have to modify it. We started by already modifying the title. We have to modify the horizontal axis because it does not start at 0. So you remember we do that under the horizontal axis option. We change the minimum value, type it in, force it to start at 0. And when you do that, if you assume that the 0, 0 would be a valid data point, notice that this graph is also going to be curved. You see that? The linear trend line is not going to be a good fit. So let's go ahead and add that trend line under the series submenu in the chart editor. See, linear is no good at all. Nothing is really on that line. So we're going to try power series next. That's what we try to do. Yeah, and power series is a great fit. But again, this is not going to be our final graph because I have a curve. So I don't want a curve. So what you need to do now is go back and look at your graphical summary sheet, which is in Google Classroom, to figure out how do you linearize a graph that looks like that. And if you recall, we actually did one that had that shape. And what did we have to do to linearize a graph that was a parabola that was concave up like that? Maddie? I'm sorry. Okay, so not really square the time, but we had to square whatever was on the x-axis. So in this case, what's on the x-axis is 1 over time. So what we're going to square is 1 over time. So we'll end up with 1 over time squared. Okay, and that's what table 4.3 is going to be. So let's go ahead and copy table 4.2 over. And we're going to have to change the formula in here. That's not a problem. So this will be table 4.3, which means we have a second linearizing step. And instead of plotting 1 over time, we said we have to plot 1 over time squared, which means our units are going to be 1 over seconds squared. Okay. Our positions are all going to remain the same. Now, how am I going to get the answer, the value, the formula for 1 over time squared? Pretty easy. I'm going to say equals, then I'm going to go back up to table 4.1. I'm going to put that value in. So I'm going to have that it equals 1 over A3 squared. 1 over A3 squared. Okay, that's the formula. So it's going back to the original data, not the data in table 4.2. I hit enter, so now I have my value in cell. My cell is A32, but now I want to autofill that all the way down the table in the 1 over time squared column, and there are my new values. Because they are looking very similar to one another, I'm going to increase the precision of this data by increasing the number of decimal places by 1, and now I can see a distinct difference between the first value and the last value. Are you all with me? Anyone need me to wait? All right, so now we're going to graph this. So let's go ahead and do that. Make a graph of position versus 1 over time squared. We're going to edit the title because this is now graph 4-3 of position versus 1 over time squared. It does start at 0 on the x-axis, which is lovely. And when I look at this, do you see how this looks much more linear now? Can you see that? Okay. So what we're going to do is add our linear trend line to this graph. And since it is now linear, that looks really good. I can now add my equation label and show the r squared. And notice that the r squared is perfect. Perfect one. All those data points fit the line that we just drew. Okay, so if in a lab you have to linearize a graph, which you do in this lab, lab 4, you have to show me all the steps to get to the linearization. You have to show me all the data tables. So show me the first data table. Show me the curve. Then show me the next data table in your attempt to linearize and that graph. And if that's also a curve, then you show me another data table with that graph that hopefully works out to be linear. I haven't seen any that require more than 2 steps to get there. This is the most cumbersome one. But having this now as a resource should help you when you have to linearize something. That's why we did it all together. I want to make sure you have it correct. So when you have to linearize a graph on a lab, you can open this up. This is why it's not under labs, it's under lab resources. You are not turning this in. I'm not looking at it. You did this for you. So now you have basically notes, electronic notes that show you how to get things and what they should look like. You follow what I'm saying? Okay. Any questions? Okay. Then let's go to your Google Sheet that you have for lab 4. Okay, you should have shared a sheet with everyone in your group so you're all working on it together. You can all make edits at the same time. That's the idea. Now, this is the graph that I think Olivia's group got, right? This is your data. Okay. And we made some modifications yesterday to get the dot number, the times, and the displacements. You're going to format this so it looks a lot prettier when you put it in your actual report that you're submitting to me. And you got a graph of displacement versus time, which looks a lot like what we see here. The equation really is irrelevant because what do we have to do with this graph? I got to linearize it. Okay. So what I'm going to do is I'm actually going to insert a row above this data table, and I'm going to call this table 1, which is displacement versus time data. Okay. I'm also going to format things so everything in this table looks nice and pretty so I can just copy and paste it into my Google Doc later by centering all the data in the cells. And I'm going to add grid lines. And to add grid lines, you'll see here on my toolbar that there is a borders button. If I click that, I can then select all borders around the numbers in the table. So that way it looks really pretty. And since now displacement is being chopped off, I can right click on the right edge of column C and that will auto fit it. So that way nothing is overlapping from one column to the next to the next. Okay. So this, since it's not linear, I'm going to call this graph 1. Because I know that's not my final graph, right? It's not my final graph. I need to try to get to a linear graph so that way I can then do the calculus with the line that you're being given. Okay, or that you're getting. So what do we have to do to linearize our graph? What do I have to do? What's the next step to linearize this? Nick? Yeah, I got to square the horizontal axis, which is time. So we're going to make data table 2. I'm going to just do it directly below. So table 2 is going to be the data for displacement versus time squared. Okay. So what I'm going to do is I'm going to come back up to table 1. I don't care about the dot numbers anymore. I just care about the times and the displacements. I'm just going to copy that over. And I'm going to put that here. I don't want to adjust the displacement. I'm going to leave that alone, but I need this time to now be time squared in seconds squared. So if you're all doing this together as a group, somebody is hopefully kind of taking charge and doing it, and the rest of you are following along, making sure that they're doing it right. And if you see that your teammate is doing it wrong, fix it. Help them out. I now have to tell it to square these numbers. So what I'm going to do is I'm going to say that equals the cell data up here, this number squared, caret 2. And now what I'm going to do is just autofill that all the way down. 1 squared is 1, and all those other numbers I think look correct, right? 9.5 squared is 0.90. So that looks good. Okay. So I have my time squared and second squared and displacement. Now I want to create a graph that goes with this table. So let me get my insert menu. Insert the chart. And there's the graph. I'm going to edit the title. So this is graph 2. That is displacement versus time squared. This looks a lot more linear than the last one. So I'm going to go ahead and now tell it, I have my 0, 0 on the bottom left. I'm going to add my trend line. Linear looks decent. Label, say use equation, and we need the r squared. So notice the r squared is not exactly 1. We don't expect it to be exactly 1 because this is real data, not made up numbers that I'm just giving you. But it's an indication that we should have a good degree of confidence in the data because it's really close to 1. You see that? 0.997, that is like really close to 1. So that's good. That is when I ask you in the lab, in your conclusions, to talk about what kind of confidence you have in the data. This is what you're doing. You're looking at 3 things in this lab. You might want to write this down somewhere so you remember when your group is writing your report, because I'm going to look for it in your conclusion. When we talk about the confidence in the data, if you are ever making a graph, got to be linear, you look at the r squared. The closer that is to 1, the more confidence you have. That's one thing. The second thing you're going to look at, let me see if I can find that file. I think this is it. I think this is your group's file, Olivia. Yep. Okay. You'll see over here that Olivia's group has this data table over here, right? With your lengths and your heights. Okay. And you were asked, I told you, you had to make, okay, you're going to number these. Those are trial numbers. Okay. So you have trial number 1, 2, 3, and 4 because you had 4 people in your group. You're going to center your data under your column headings. We always do that. And then what we have to make sure is that all of the data has the same precision. All her lengths went to the 100th of a centimeter, which is what you can measure to with a meter stick. All the heights, same thing, to the 100th of a centimeter. If they're chopping off, you now know how to add that additional decimal place into the table, right? We talked about that in the linearization lab. Okay, now look down here. There's a standard deviation. You got the average. The average always has the same precision as the data. So does the standard deviation. So you've got way too many decimal places on those standard deviations. How many decimal places should the standard deviations go to then? How many decimal places to the right of the point? 2, because all the data went to the hundredths. These are in centimeters. Everything there is in centimeters. Okay, so your standard deviation for your length was 0.06 centimeters. To determine how confident you are in that standard deviation is an indication of how clumped up the data points are to one another. You remember when you did your target practice lab? We said precision occurs when they all drop in the same exact spot, right? They're all clumped together. A small standard deviation, 0.06 centimeters compared to the average of 106.93, should give us really high confidence because you compare the standard deviation to the average measurement. Since it's really close, it's a very small percentage of the average. That gives you a high confidence in the data you collected for your length. Look about your height. The average height was 14.34 centimeters, and the standard deviation for this group was 0.26 centimeters. That's also a small percentage of the average. So there's good confidence, but are you as confident in your average height as you are in your average length? No. Why not? Why are we not as confident in the height measurements as we are in the length, Ruben? Yeah, it is a bigger percentage of the average compared to the length standard deviation compared to the average. You always compare the standard deviation to the average measurement. So since they're still small percentages, does that give you a lot of confidence in your data that you collected? It should. It was very repeatable. Okay, if it's a large standard deviation compared to the average, then you're not going to have a lot of confidence in the data you collected. Very random. That's not good. Okay. Your percent difference or percent error that you're going to do in this lab has nothing to do with how confident you are in the data you collected. One of the questions you answer in every conclusion like this is how confident you are in the data collected. So in this lab, you're going to look at 3 things to determine your confidence. What are those 3 things? See if you've been paying attention. What are the 3 things you're going to talk about that give you confidence in the data for this lab? R squared. Standard deviation for length and for height. That's 3 things. That's what you're going to talk about. That's it. Now in this lab, and I'm going to go back to the other lab, my sheet, this one here. To determine your velocity and your acceleration of the car as function of times, which they ask you to do, you're going to use the equation that you got from this Google Sheet. Okay, so what I'm going to do is copy this down and we're going to go over what we're going to do with this. Because you then also have to figure out what was the acceleration of gravity according to this lab. And we'll talk about how to do that. So this equation that this Google Sheet gave me for the linear was y equals 92.5x plus 3.81. And on the graph, I have the displacement On the y-axis in centimeters. And on the x-axis, I have time squared in seconds squared. And that gave me my line. Okay. So let me shift over to my document camera so we can now look at this. This is what we're looking at. So on the y-axis, I have the displacement. This is the slope of that line. The slope of this line is in centimeters per second squared. On the x squared, I have the time squared. And this is the y-intercept, which is measured in centimeters. To get the velocity, what are you going to do? What are you going to do to get the velocity equation, Ruben? Yep, take the derivative. And then to get your acceleration equation, what are you going to do? Take another derivative. Okay? Now, I'm just going to do a hypothetical. Actually, I can tell you what it is right now. I know what the acceleration is for this group. They got 185 centimeters per second squared. Okay. You're going to have to convert that to meters. You are tasked in this lab with determining what the acceleration of gravity is. And in the lab handout, it told you how to get it. What do you do to get G with the data you collected? Lab handout, lab 4. I just tell you, right now, I feel like nobody read anything because I'm asking questions. You're like, no idea. That's not a good feeling as a college instructor right now. What do you do to get the acceleration of gravity? According to the lab handout, what does it say to do? Yes. So what does it give you for the equation for G? Okay, AL over H. This is the value of A. L is going to be the average measurement. Olivia, look at your Google Sheet. Can you tell me what your average length was? Centimeters. And what was your average height? 14.34. All right. You're going to leave those in centimeters because as soon as I plug in centimeters here and centimeters here, what happens to the centimeters? They cancel out. So all this group has to do is take the 1.85 meter per second squared, multiply by 106.93 centimeters, and then divide by 14.34 centimeters to determine what their value of G is. You are asked then how accurate your result is. This is your experimental value. What value do we use as our accepted value in AP? 9.8. So you're going to have to calculate and show a % error for this lab. And then you have to explain why you're not getting 9.8. And you're probably not going to get anything close to it. There's a lot of very specific errors that occurred in this lab. And you're going to have to figure out what they were and use proper measurement terminology. When you write your conclusion about the errors, I want you to make sure you look back at the example lab I wrote. It should be formatted just like that. There was this error. This is what this error is. This is how it presented itself in this lab. This is how we minimize that error moving forward. You need to be ultra specific with me. Okay? And one of the ways we minimize errors in every lab, wow, I'm giving you the answer for like everything here, is you increase the number of trials that you do. So instead of doing 4 length measurements, you would have done like 15. Instead of doing 4 height measurements, do 15 or 50. Instead of doing 1 ticker tape for the same ramp, how many could you have done? 4 people in the group, do 4 of them, and then average those numbers together and see what you get. But you looked at one trial. I want you to think about this. Whenever we test a new drug that's produced, do we just test it on one person and say, great, it worked, let's give it to everybody? No, we don't. You got to test it across millions of samples. You increase your sample size. And what that does is it gives you much smaller standard deviations, much higher confidence in the data, and it gives you a much better average measurement. Because if you think about it, you do one trial and it's messed up. That one trial's average, that one trial is the average. This average acceleration came from one run of the cart down the ramp. If you had done 50 runs, do you think you're going to get 185 centimeter per second squared? Probably not. So if your one run is messed up, now everything's really messed up. Okay, so that's why we increase the number of trials to minimize the uncertainties present in the lab. You need to talk about that in every single lab report. Because honestly, do I have time to let you run that cart down the ramp 100 times? Nor do you want to. But that is going to be asked on your AP exam. Guaranteed. What can you do to minimize errors in the lab? That is one of those questions that comes from the linearizing graph. It's an experimental design question. You have to design the lab. Then they're going to give you the data, which is not linear. How do you linearize it? They're going to ask you, what are you going to plot? And then, oh, look at this. This was the measurement they got from the graph. They're going to give you a hypothetical number. But it was supposed to be this. What could you do to minimize the errors in the lab? And what are you going to tell them? Do more trials. And why? Because they're going to ask you why. What are you going to do and why? You're going to do more trials because it does what? Crickets. I don't want to hear crickets. Minimizes the uncertainties and gets the average closer to the real average of what the data is. Okay, that is your standard answer. I've just told you the answer to one of your questions on the AP exam. You're welcome. It's only September. I'm getting you ready for May. That question is the question you're going to bank on because the other 3 are held. You're going to look for that question first. You're going to know what question number it is. And you're going to do that question first because you can get it right 100%. The others are crapshoots. It's just the way it is. One of them is predictable. The other 3 are not. You'll see when we start reviewing. And you'll see when I start giving you exams, your chapter tests. I'm going to start throwing these at you. Don't be surprised if your first test on chapter 2 and 3 has an experimental design question where I ask you the same kinds of stuff. I want to make sure you're paying attention. I want to make sure you know the answer already, especially since I just gave you the answer. Okay. Any questions on this? All right, so now you know how to finish lab 4. And now you gotta get lab 3 done too. Lab 3 is due Monday, lab 4 is due Tuesday. 1 for each. Lab 3 is for the partnership, you're working with one other person. And lab 4 is for the group, 1 per group. Do not turn it in unless you are submitting the report. So I should not see, we had 6 groups for lab 4, I should get 6 turned in, not 15. I know you want it off your to-do list. It's not going to happen because I'm going to return it to you without a grade. And then it'll go back in your to-do list. Sorry. Just ignore it. Okay. The rest of the time you have now is to work on these labs. Make sure for tomorrow that you are reading lab 5 and 6 so that way you know what the heck we're doing in class tomorrow. Okay. And make sure you're also watching the chapter 3 video that is posted attached to this assignment for tomorrow, right? Because you have assignments for chapter 3 that start next week. Okay. And I'm sorry, I won't be here to go over those with you. Mr. Walter will be the one going through those with you if you need it. All right. So I'll let you guys work.